dear students, I hope you will be okay. And now start our course about the WHDL modeling. At first, is there any question? If there is any question, please type it in chat space. If not, we can start our speaking about the course. Good evening to you. Okay, at first, we need more example to learn more about the entity. Okay, no problem. As you know, in this week, I send you, I think, 5 sessions of the course, and I will send you more. Yes, I will send you more. What about the example? Let me to send you some examples or some exercise for you to learn more about the entity and architecture. No problem. Only please remind me in this week or next week. I will send you some examples or exercise to learn more about the entity. Okay. We speak about the entity and architecture in previous session, and now we want to speak about some examples about the entity and architecture, and then we want to continue our course. Okay. وقت شما هم بخیر، متشکرم. سلام به همه شما. خب، now let me to start our course at first. Okay, now you have both the voice, my voice, and my desktop. Is it right? Is it okay? we start some examples about the entity and architecture. At first, we start by a very simple example. This simple example is a circuit like this. We know that this digital circuit has 3 inputs. This, and this, and 1 output. No, 2 outputs. This circuit is really a 3 input NAND and NOR gate. Inputs are, for example, A, B, and C. And the outputs are NA, it means NAND, and NO, it means NOR. Okay, that's very simple. And now we want to start this at first by entity. Entity, name of the circuit. For example, NAND and NOR inputs. NaNO3 is okay. After this, port. And now we must write the name of inputs and outputs. We'll start by the inputs. A, B, and C. All of them are inputs in, and all of them are standard logic. The other is NA and NO. Both of them are output bits, and both of them are standard logic. And at the end, entity. Okay, after this, we can write the architecture. Name of architecture, for example, behavioral, we can write BEH as behavioral of NA NO3 is, and we can start by begin. Okay, now we must write the signal assignment for NA and NO. What about NA? Is the NAND of the 3 inputs. NAND means not and. Then we must write not of A and B and C. better to use from parentheses to specify order of operation, the order of function. At first, B and C, and then A and B and C, and then not. NAND means not and the other NO means not or. Then it is not of A or with B or with C. Okay, it is sufficient, and now we can write AND architecture or behavioral. And this is the end of this circuit. Do you understand? Is it clear? Okay. And now we want to speak about a special signal assignment. We say this conditional signal assignment. What about the conditional signal assignment? It means it's such an assignment that needs some of the students need translating. It is only a simple example. Do you need for this simple example translation? Mr. Ahmad Muhammad Abdul Hussein. Okay, after some speakings, I want some of the students to translate for other students. Let me to see the name of the students at first. Who can translate my speakings into Arabic? Is there anyone? Is there anyone to translate my speakings from English to Arabic? Or from Persian to Arabic? Okay, very good. Then I think you can use from this, is it? That's very good. Okay, now we can continue our speaking. We have another signal assignment that we say conditional signal assignment. Conditional signal assignment means a signal assignment that uses from one or more to three conditions. Like a very simple, for example, multiplexer. A multiplexer, we have here a multiplexer with three inputs. Two inputs at first. This three, this third input, and one output. Okay. It's a multiplexer. A multiplexer. That is 2 to 1. It means that it has two inputs. It selects one of them and sends them to output. For example, this is the first input, I0. This is the second input, I1. And this is the select input. We can write it by S. Select one of the inputs, for example, 0 or 1. And this is the output, F. For example, we speak about the operation of this multiplexer. We say that if select is 0, then F must be I0. And if select will be 1, then F must be I1. This is the explanation of the operation of this circuit. Now we want to write the entity and then architecture of this circuit. Entity marks 2 to 1 is port I0, I1 and S. All of them are input bits and they are a standard logic. And the other is F. This is output bit. And this is a standard logic 2. And entity or marks. F is output, but S is input because S is a select input. It selects, for example, it has a value 0 or 1. By 0 it selects I0, by 1 it selects I1 to the output. Okay? Do you understand? Okay. Okay, this is the entity of the circuit. This is the entity declaration. And now we want to I will told you some example about the STD logic vector. As I told you, we can have both bit and a standard logic bit vector and a standard logic vector. Both of them are very similar together, but as I told you, a standard logic is better for simulation purposes than the bit, because bit only have 0 and 1, but a standard logic has more values, 0, 1, high impedance, for example, and don't care, high, low, weak, high, weak, low, and etc. And this is better to select a standard logic than only bit or bit vector. Okay? Do you understand? Very good. Okay, now we want to continue. Very good. Now we want to continue by architecture. Behavioral of Marx 221 is begin, and this is the architecture. We must write like this: F is I0 when, this is the conditional signal assignment, when S is 0, else will be I1 if my voice has cut off, please tell me to repeat for you, speaking for you, no problem. Okay, if F is I0 when S is 0, else F will be I1 when S will be 1, else, as I told you, because S is a standard logic, it may have some other values, and now we must specify other conditions. Then I will write like this: 0 when other values, like this, and then and behavior. As you can see, I0, I1, S, all of them are input, no problem. Like this port, I0, I1, S, input, a standard logic. F is output, out, a standard logic. For your question, Mr. Qasim Hadi Isa. And the other, F is I0 when S is 0. Else, F is I1 when S is 1. Else F will be 0. It means that if S won't be 0 or 1, for example, don't care. For example, high impedance or something like that, F must be 0. Do you understand this example? Okay, Mrs. Zainab Kazem Jaber. Let me to, at first, we have two steps. The The first step is speaking about the entity. For example, entity MUX221 is port I0, I1S, all of them are input and standard logic. F is output and standard logic, and end entity. Do you also understand this step until this? Mrs. Zainab Kazem. Okay. Now, as I told you, if S is 0, F will be I0. If S is 1, F must be I1. Okay, we can write it by conditional signal assignment, like this. Architecture begin F. F is I0. When, this is a keyword in VHDL, S is 0. Else is another keyword. F will be I1 when S is 1. Else, and the third line means that if S is not both 0 or 1, for example, it is high impedance. It is, for example, maybe undefined number or something like this, F must be 0. Then in this situation, F is not I0, F will not or won't be I1, F must be only 0. This is the next else, like this. Then if S won't be 0 or 1, else F must be 0 and behavioral. Okay, very good. Okay, now we want to take you another example. Let me to go to the slides. Yes, as I told you, conditional signal assignment, and a very good example is multiplexer. And you can see that the order of condition is very important in this situation, because if the first condition will be true, the final value must be, for example, A, and we don't check another conditions. Okay, the order of condition is important. Another example is another multiplexer. This multiplexer is a 4-to-1 multiplexer. This multiplexer have 4 inputs, A, B, C, D, and 2 select inputs, S1 and S0, and 1 output, M. Then entity MUX4 is port A, B, C, D, all of them are inputs, S1 and S0 input, M output, and entity, and architecture. Architecture behavioral of MUX4 is begin with M. M is A when both of the select inputs are 0. Then S1 is 0 and S0 is 0. Else M will be B when S1 is 0 and S0 is 1. Else C when S1 is 1 and S0 is 0. B when S1 is 1 and S0 is 1. Else means if the S1 and S0 have other other situations. We use from this special expression unaffected. What does it mean unaffected? It means that if the select inputs have a value other than 0 or 1, the output must be unaffected, or the output must hold its previous value and don't change or doesn't change in this situation. Okay, then we can go back here. Then unaffected means that the output must contain its previous value and doesn't change its value in this situation. Okay. This is the meaning of unaffected. Then you can see that if we have another situation or if they have another condition, M won't change and M contain its previous value. It means unaffected. And at the end behavior on. And we can have a total result. It means that M must have a latch because this latch is necessary for unaffected, for containing its previous value. Okay. Do you understand? Okay, one of the students write 50-50. If other students understand the speakings, I can enable microphone to translate for all the class. Input S is a select input. For multiplexers, it is necessary. It is a part of the system. The multiplexers. We must know about the multiplexers. It is a part of digital design. there anyone to enable the microphone to speak in the class, to translate Arabic for the class? Okay, then if you use from the translator, what is your question? If there is any special question, write for me to explain for you. Okay, there is not any question? Then we can continue. Another signal assignment or selecting signal assignment is like case in programming. For example, multiplexer. This multiplexer is like the previous multiplexer. Both of them are like together. But the only difference is difference by this instruction. We can write with S. S is a 2-bit number. Here S in STD logic vector 1 down to 0. With S select. M is 1. M is A when 0, 0. B when 0, 1. C when 1, 0. D when other. Other mean other states. And end behavior. Then this is another example or another case for selecting different conditions for the signals. Do you understand? Okay, and two, what do you mean M2 SUECH? What does it mean? I don't know. Mr. Muhammad Jafar, I don't know what do you mean and to. What do you mean? And to chi? And to what? What is your question? Please repeat your question. Mr. Muhammad Jafar Yasin Al-Shabibi. Please repeat your question. No question. Okay. Then another thing, another discussion about the HDL coding is a definition of intermediate signals. For example, let me to have another example. Let me to use from this slide. For example, here we have A, B, and C as the inputs, and F as the output. For example, this entity, its name is F, for example. Entity F is port A, B, and C as the inputs, and F as the output. We know that we have two signals here. We can have two signals here, W1 and W2. W1 is A and B. W2 is not B and C. And F is W1 or with W2. We can use by W1 and W2 a simple and better racial coding. Then this is better to define two mediate signals for this code. Then how can we define this signal? By signal keyword between architecture and begin. We must write signal W1 and W2, the name of the signals, and the type of the signal, a standard logic, and tamam, and finish. Then now we can write by W1 and W2. Begin, and W1 is A and B. W2 is not B and C. F is W1 or with W2. And end behavioral. Okay. This is a simple example for definition of mediate signals. Do you understand? Yes, Mr. Muhammad Jafar. At first, this multiplexer have 4 inputs and 2 another inputs for selection. Then all the inputs are 6 inputs for multiplexer. Okay? In the entity, only the definition of inputs and outputs, and within the architecture is the work of what happens inside the electrical. Yes, really that's exactly right. Unaffected. Output must contain its previous value and doesn't change its value in this station. Yes, it is unaffected. No, doctor, can you repeat, please? Okay, I want to repeat it for you. Let me to told you a simple example. Consider that we want to let me some minutes. Consider that we want to write the VHDL code of this figure. We know that we have three inputs, A, B, and C. We have two outputs, sum and cout. But here we have some other signals here. One signal here, like this. This is, for example, W1. Another signal here is this. Here. Another signal here is here. This is another signal. Another signal here is another signal. These are some mediate signals. This signal is, for example, W2. W2. This signal is W3. These are some wires, but they can help us to write a better and simple code. Okay? How can we write a simple code by these signals? We want to write this. We want to speak about this. Architecture. For example, data flow or full adder is. Before begin, we must find these wires or these signals by a keyword, signal, and the name of the signals, W1, W2, and W3, and the type of the signals, a standard logic. After this, we can continue our VHDL coding. Begin. And now we can write the codes. For example, W1. What about W1? W1 is XOR between A and B. A XOR B. And sum. Sum is XOR between W1 and C. And W2. W2 is AND between W1 and C. W2. And W3 is AND between A and B. And the output carry is OR between W1, W2 and W3. And data flow. Then by using these signals, these mediate signals, mediate signals, not inputs, not outputs. By using these signals, we can write a simple VHDL code. And how can we define these mediate signals? By this keyboard. Do you understand? Yes, S is sum. All of you, do you understand? Is that clear? Yes, Cout is OR between W2 and W3. Slide 30. Yes, it is a little mistake between the figure and the writing, the code writing. We use from S1 and S2, but as I told you in the code S1 and S0, you can change them. We must change this figure. It must be, for example, S1 and S0. No. W1, W2, and W3, all of them must be in architecture, not entity, because entity contain only inputs and outputs, but these mediate signals are not inputs or outputs. Okay, that's right. Okay, now we can go here and continue. Okay. It is a very simple explanation about the resolve signals. A resolve signal is a special expression in VHDL. When we have different values and assigning different values to a one signal, we need a table assignment. For example, like this. A table assignment. Let me write for you a table assignment like this. For example, we want to write a table. We know that the standard logic has different values, and we must specify these different values. I only specify some of them for you, because only I want to show you the assignment table as an example for you. Okay, for example, we want to write the assign table for AND operation and or and etc. Know that each standard logic has some different values. For example, 0, 1, high impedance, don't care, high or weak high, and etc. Low and etc. And we know that when we want to add two standard logics, we have for the second logic another values like them. High impedance, high, don't care, and etc. Okay. When we add two standard logic with 0 value, the output must be 0. If one of them is 0 and the other is 1, the output must be 0. If one of them is 0 and the other is high impedance, the output will be 0. 0, 0, 0. But if one of the inputs is 1 and the other is 0, the output will be 0. If both of them are 1, the output is 1. If one of them is 1 and the other is high impedance, the output, for example, must be high impedance, or don't care, or high and low. And if one of them is high impedance, we must write with respect to others. If both of them are high impedance, then the output must be high impedance. If one of them is a high impedance and the other is don't care, the output will be undefined. If one of them is high and the other is high impedance, the output will be high impedance. If one of them is low and the other is 0 for the high impedance, the output will be low, for example. Then you can see that we have a table, a result table. Then we will know the output value. But we have some signals that they don't have table assignment. We call these signals unresolved signals. Okay? Then we we have some, or we have signal type without table assignment. We call these signals unresolved signals. One of them is STD logic and STD logic vector. In some special situations, we can use from these signals. Then, in some situations, the VHDL coder can use from these signals. Then for you and many VHDL coders, it is better don't use from these signals. If anyone use, he can write from this special signal and he or she must write the table assignment or must specify the table assignment. The only benefit of using this signal is that you can specify this table assignment. Then it depends on you, not it depends on VHDL. The only difference is that the table assignment for a standard logic and a standard logic vector is defined by the VHDL. But for STDU logic and STDU logic vector can be defined by the writer. The only difference is that, okay, you understand? As I told you, Z is high impedance, H is weak high, L is weak low, and I explained all of them in the previous session, in the previous course. And as I told you in the previous course, I told you that a standard logic and a standard logic vector, both of them are very similar to bit and bit vector, but for simulation goals and simulation works, it is better to use from a standard logic and a standard logic vector. We can have STDU logic and STDU logic vector. The only difference is that the VHDL specify the table assignment for STD logic and STD logic vector, but you must specify the table assignment for STDU logic and STDU logic vector. Okay. I think the explanation is sufficient. And now we can go to another lecture. Okay. In this lecture, at first, we have some examples here. These examples help us to have a better view to entity and architecture. I suggest to you that see these examples. See all of them. They help you to have a better view to entity and architecture. For example, one of them, this is one of them, 4-bit multiplexer. We call it quad multiplexer, QMUX. This is a 4-bit has 0 input. Another 4-bit has another input. 2 4-bit inputs. 1 select input. And 1 4-bit output. And we must select one of the 4-bit inputs and send it to output. It is a special question or example. Another is decoder. The only thing is that we use from this operator, ampersand. Ampersand is concatenating 2 bits or concatenating operation. What does it mean, concatenating operation? Let me to explain for you. For example, here we have 2 single bits. For example, X as 1 bit and Y as another bit. When we say, for example, Z is X ampersand with Y, it means that we have or we use like this. We have a 2-bit number with name Z, and we specify X as the first bit of Z, and we specify Y as the second bit of Z, like this. Then we have a 2-bit number with X as the first bit and Y as the second bit. Okay, do you understand this? Okay, very good. And the other example after decoder is encoder. As you can see, this encoder like this. We have 4 inputs, for example F0, F1, F2 and F3, and 2 outputs. For example X and Y. We consider immediate signal as W. When we write W0, it means that the 0 bit of W must be X, and the 1 bit or first bit of W must be Y. and it is obvious. The other thing is that when we write, for example, like this, in this instruction, the first condition, if the first condition will be satisfied, will be true, W will be 0, 0. For example, if F0 will be 1, W will be 0, 0. If not, it looks to F1. If F1 will be 1, W will be 0, 1. If F2 will be 1, W will be 1, 0, and etc. In encoder, the encoder works or in reverse with decoder. We say that only one of the inputs must be 1 and the others must be 0. If we have a situation that all the inputs, for example, or 2 inputs or 3 inputs will be 1, by this definition, it looks to F0 at first. Then, if F0 will be 1, then if F0 will be 1, it doesn't look to other lines, to other inputs, and W will be 0, 0. We call this priority. Priority, or in Persian we say أولويات. Then we have an encoder with priority. With such priority with low priority, because in the conditions at first we start by low line 0, 1, 2 and then 3 with low number priority. At first we check F0 and then we check F1 and then we check F2 and then we check F3. Okay? Do you understand this? Is it clear for you? Okay, very good, very good. We can have another kind of encoder. Encoder with high priority. With a high priority. But how? Do you know? You can write it as an exercise. Okay? Please write it as an exercise. We can have an encoder with high priority. You can change this encoder 4 to 2. You can change this encoder to be a high priority encoder. Okay? Please do it as an exercise. Very good. Very good. Okay. We speak up to delay modeling. Very good. And we can continue delay modeling in the next session. If there is any question, please ask me. If not, we can end up our class. Okay, very good. Thank you very much. And you, and have a good night. I hope to have all of you have a good night. And thank you very much. What do you need from us? Yes, yes. Encoder with high priority. Yes. As your exercise, yes. I suggest to one of you that write this exercise, not the solution, only the question of the exercise in the group, in embedded system group, to see all the students. You can write it in Arabic, to see all the students in Arabic. You're welcome, and thank you from you. Thank you very much. Goodbye.